All right, so here we're looking at intermolecular forces, for which the first question asks that we state what is the strongest intermolecular force present on each of the following molecules. And this is a really useful activity as it can give us more information about the physical properties of these molecules, which is what's asked in part B. So here we have CH4, H2O, H2CO. Very first thing we want to do is put down the Lewis structures, because when we're thinking about intermolecular forces, the key question is about polarity. And to know about polarity, we need to know what it looks like. So here are the structures of each of these three molecules, and we want to conclude, is this a polar molecule, as that will help us to determine whether or not there is a net dipole and therefore dipole-dipole force is present, or if there are not. And we want to consider if there is hydrogen bonding present as well. So that might sound like a lot, but again, the key is polarity. Methane, CH4, is nonpolar. It has CH bonds. They're all symmetrical, all the same bond polarity, and therefore will cancel. Water is polar and notably also has this OH bond, which we're going to talk about soon. And formaldehyde, H2CO, is simply polar. No OH bond, NH bond, or HF bond, which helps us conclude that methane has only London dispersion, being nonpolar. Water is polar with one of these types of bonds that will make hydrogen bonding, and therefore hydrogen bonding is the strongest intermolecular force present here. Remember that that will be on a molecule with either a HF, hydrogen fluorine, HO, hydrogen oxygen, or HN, hydrogen nitrogen bond will have hydrogen bonding present, which is different than just simply dipole-dipole, which is from a polar molecule with no hydrogen bonding. All right, so we've determined the strongest intermolecular force, which one has the highest boiling point. And an important caveat of this is that all of these have pretty similar molar masses. You know, it is different, right? Methane is about 16, water is about 18, and formaldehyde is about 30. But for all intents and purposes, these are effectively the same. You know, it's not like one of them is 300 and the other one is 30. That would really need to be considered differently. So roughly the same molar mass, so we don't expect that to be a factor. It would be if we were comparing, you know, the London dispersion force on a really big molecule versus a smaller molecule. The really big molecule really would have a lot more intermolecular force by virtue of its molar mass. But these are pretty similar, so we can take just the intermolecular forces that we've laid out so far. Hydrogen bonding is the strongest intermolecular force. London dispersion is the weakest, and therefore the lowest boiling point is going to be water. It is the least strongly held together by its intermolecular forces. Therefore, will begin to boil at the lowest temperature. Smallest amount of kinetic energy needed to overcome the intermolecular forces. Highest is water. Hydrogen bonding is the strongest intermolecular force, and therefore will need more temperature for it to boil, overcome its intermolecular forces. And this is true in practice as well. Methane is a gas at room temperature, so it's boiled well before a temperature that is room temperature. Water is a liquid, and it doesn't boil until 100 degrees Celsius. And formaldehyde is kind of in the middle. It's a liquid. It is volatile, so if you're in a room with formaldehyde, you'll smell it. That means that there are particles that are escaping, and you can smell them. You can smell water too, but it's a more volatile liquid, kind of like gasoline or alcohol are more volatile liquids. They would boil at a lower temperature, and even at the temperature that you're at, they will be able to be in the gas phase more readily. Okay, so next we want to say a slightly different problem, which is how can we calculate the amount of energy that's required to bring a mixture of ice in water at 0 degrees Celsius to water at 27 degrees Celsius. And the most important thing when looking at these mixed phase thermodynamic type problems is what is the path that we're taking? What is happening to the water in this system? Because we want to know about the energy, but we can't just lump together processes like melting and warming. We have to consider them separately, and then we can add their energies at the end. And so here, the first thing we need to do is we need to melt that ice. So we need to go from a mixture of ice and water to all water at 0 degrees Celsius. This means that we need to melt the 50 grams of ice that's in the water. Then, once it's all water, 300 grams of water, that ice is turned into water, we need to warm all that up to 27 degrees Celsius. So two things we need to calculate, and we need to identify how we calculate the energy associated with each of these processes. So the first is Q1, we'll call it. Q1 is equal to the enthalpy of fusion, this is melting or freezing, multiplied by the number of moles that are involved. And we can see that from the definition of delta H fusion in the table above. And Q2 is a warming process, so MC delta T. The mass times the specific heat of water times the change in temperature will give us the energy associated with process 2. Let's look at Q1 first. N is 2.78 moles. This is 50 grams of ice. Ice is H2O. We've converted it to moles. Enthalpy of fusion is 6.01 kilojoules per mole. We go ahead and plug into our equation. Note that we really get this equation just from the enthalpy of fusion alone. It's 6.01 kilojoules per 1 mole. So to get the number of moles that we're interested in, we simply multiply, and we see that 16.7 kilojoules will be required for part 1. For part 2, Q2, it's an MC delta T process. So the mass is 300 grams. We have the specific heat of water. We're increasing 27 degrees Celsius. We plug in, and we see that Q2 is equal to 33,000-ish joules, or 33.9 kilojoules, just to go ahead and unite our units here. We're not quite done because the total Q water is Q1 plus Q2. Both of these things need to occur to get to the point we're interested in. And that means Q water here is positive 50.6 kilojoules. The last question wants us to say, well, if that warming of the water that occurred is actually coming from a hot iron rod into the ice water, what is the initial temperature of this really hot iron rod? So this is a calorimetry problem, and we're going to assume that all of the heat from the rod goes into the ice water. And note that the amount of heat we've already calculated from the previous question. That's Q water, 50.6 kilojoules. That's the energy that went into the water from the iron rod. And so in any system like this, we want to anchor our knowledge on this equation. 0 equals all the heat and energy processes that are associated. This is conservation of energy, and this is saying that the heat can't go anywhere else other from the water into the iron, or rather from the iron into the water, excuse me, and is really a good practice. This is kind of a simple case, so just jumping to this may be tempting, but stating it as a conservation statement really will help if there's more complicated systems that you're considering. From that, we know Q water, so Q iron is negative 50,600 joules. Water gained 50,600 joules, iron lost 50,600 joules. Another Q equals MC delta T process. In this case, the variables are a little different. I would highly recommend that you not plunk in the initial temperature at this time. Just calculate delta T as its own variable, change in temperature, using the following. We plug in, we get that the change in temperature was negative 751 degrees Celsius. This iron rod dropped 751 degrees Celsius. From here, T final minus T initial. The final temperature is known to be 27. This is from the initial problem. The initial temperature is what we're looking to solve for, and we know the change, and then we can conclude that the initial temperature must have been 27 higher than 751, or 778 degrees Celsius.